Hello, welcome to another module in this massive open online course. Let us continue our discussion regarding the mathematical preliminaries for the framework of convex optimization, looking at another very important concept, that is of the eigenvalues, the eigenvectors and eigenvalues of square matrices. Right. So, we are going to start talking about the concept of, or rather the concepts of eigenvectors and eigenvalues. Okay. And now these is the eigenvector, the notion of eigenvector and eigenvalue is defined for a square matrix, correct. So, for a square matrix A, all right, x bar is an eigenvector x bar is an eigenvector if we have A x bar, that is the product of the matrix A with the vector x bar, A x bar equals a multiple of, that is lambda times x bar, all right, and this is a fundamental equation for the eigenvector, all right, and well, this lambda is known as the eigenvalue, this is known as the eigenvalue, and this vector x bar is known as the eigenvector. Okay. And now, since A x bar equals lambda x bar, that implies A x bar equals lambda times, I can use the identity matrix here, times x bar, which implies A x bar minus lambda I times x bar equal to 0, which basically implies that A minus lambda I times x bar equal to 0. Now, this implies, what this means is, this matrix A minus lambda I, this is a singular matrix. There exists a vector such that A minus lambda I times x bar equal to 0, which implies that the determinant of A minus lambda I equals 0. Okay. So, we use this to denote the determinant. Okay. So, if lambda is an eigenvalue of A, that means the determinant of A minus lambda I equals 0. Now, by evaluating the determinant, you can derive an equation that is known as the characteristic equation corresponding to the matrix A, and the roots of that, all right, the roots of this equation in lambda give the eigenvalues of the matrix A, all right. So, this gives, so this basically gives the characteristic polynomial, correct. So, A minus determinant of A minus lambda I, this gives you the characteristic polynomial, of A in terms of lambda, and the roots of the characteristic polynomial these are the roots of the characteristic polynomial are the eigenvalues of A. For example, let us say A is the matrix 1 1 1 minus 1. Let us take this simple 2 cross 2 matrix. Okay. All right. So, this is a square matrix A. And now we want to find the eigenvalues. Okay, for this given matrix A, 2 cross 2 matrix, we want to find the eigenvalues and also the corresponding eigenvectors. Okay, so find eigenvalues and the eigenvectors of A. Now, we are given A. Now, let us start by considering A minus lambda I, that will be equal to 1 1 1 minus 1 minus lambda times 1 0 0 1, which is equal to 1 minus lambda 1 1 minus 1 minus lambda. All right, and now we have to consider the determinant of this. Now, determinant of A minus lambda I equals 0. Now, if you compute the determinant of A minus lambda I, you will see this implies 1 minus lambda into minus 1 minus lambda minus of 1, this is equal to 0, which basically implies that minus of 1 minus lambda into 1 plus lambda equal to 1, which implies that lambda square minus 1 equal to 1, which implies lambda equals plus or minus square root of 2. So, these are the eigenvalues of A. Lambda equals plus or minus square root of 2. These are the eigenvalues of the matrix A. Okay, so we have got two eigenvalues, that is lambda equals either plus square root of 2 or minus square root of 2. Okay. Now, let us find the corresponding eigenvectors of the matrix A corresponding to both these eigenvalues. Okay. Now, the eigenvector, to find the eigenvector, okay, what we are going to do is we have 1 1 1 minus 1 A times x bar equals square root of 2, the eigenvalue square root of 2 times x bar. This is from the definition of eigenvalue. This implies now you can, which is also basically square root of 2. Now, you can insert an identity times x bar, which implies, now you bring it this on the left. So, this will become A minus square root of 2 times identity, which is 1 minus square root of 2 1 1 minus 1 minus square root of 2 into x bar. Now, I will write x bar as a vector, it is a 2-dimensional vector x1 x2 equal to 0. Now, this implies that you get equations in x1 and x2, 1 minus square root of 2 into x1 plus x2 equal to 0, okay, and x1 minus 1 plus square root of 2 into x2 into 0. Now, this equation, if you multiply by 1 minus square root of 2, you will realize that you get again the same equation. So, this will be 1 minus square root of 2 into x1 minus 1 plus square root of 2 into 1 minus square root of 2. So, this minus of minus 1. So, that is plus 1 plus x2 equal to 0. So, implies that basically the first and the second equation are identical, alright. So, basically you have just one equation and therefore, this has an infinite number of solutions, and that is kind of obvious because if the eigenvector corresponding to eigenvalue is not unique, that is if x bar is an eigenvector, then x bar scaled by any constant k is also an eigenvector corresponding to the same eigenvalue, okay, and therefore there is infinite number of eigenvectors in that sense, okay. So, this means that these two equations are basically the same. Now, what we will do is to derive a solution, you set x1 to derive any solution or one such solution, you set x1 equal to 1, this implies x2 equals minus of 1 minus root 2, and this you can verify is an eigenvector. That is, if you look at x bar equals x1 x2, that is 1 minus 1 minus root 2, that is root 2 minus 1, or not minus 1 plus root 2 or root 2 minus 1, and this you can check, this is one of the eigenvectors of A, okay. One of the eigenvectors of matrix, and you can check this, okay. Let us do that. If you look at A times x bar, that is equal to 1 1 1 minus 1 times x bar, that is 1 root 2 minus 1. So, this will be 1 into 1 plus root 2 minus 1. So, this will be root 2, 1 into 1 minus root 2 minus 1. So, this will be 2 minus root 2, which if you pull out this constant square root of 2, this will be, well, 1 square root of 2 minus 1, and which is basically nothing but, if you call this as your x bar, this is nothing but lambda times x bar, where what is lambda? Lambda equals square root of 2, and we already seen x bar is 1 square root of 2 minus 1. So, this verifies that square root of 2 equals the eigenvalue, and the fact that 1 comma, it verifies both, right, and that 1 comma square root of 2 minus 1 equals an eigenvector, okay. So, this verifies basically both the facts that square root of 2 is the eigenvalue of this matrix A, and square root of 1 square root of 2 minus 1 is the eigenvector. Now, similarly, one can find the other eigenvector, alright, corresponding to eigenvalue minus square root of 2. Similarly, Similarly, for eigenvalue minus square root of 2, we have 1, 1, 1, minus 1 of x bar equals minus square root of 2 x bar. This implies 1, 1, 1, minus 1 plus square root of 2 times identity into x bar equals 0. This implies that basically if you look at this implies 1 plus square root of 2, 1, 1 minus 1 plus square root of 2 into the vector x bar that is x1, x2, this is equal to 0, and this implies basically 1 plus square root of 2 times x1 plus x2 equal to 0, and you can see both the equations will reduce to the same thing. And now once again what we will do is we will set x1 equals 1, that implies x2 equals minus of 1 plus square root of 2 or minus 1 minus root 2, and therefore the eigenvector x bar equals 1 minus 1 minus root 2. Okay, so this is the other eigenvector corresponding to eigenvalue minus square root of 2. This is the other eigenvector. Corresponding to the other eigenvalue minus square root of 2. Alright, so that is a brief introduction to the concept of eigenvectors and eigenvalues of a matrix. Let us look at another important concept, that is the concept of symmetric and Hermitian symmetric matrices or Hermitian matrices. Alright, so what we want to look at now is basically the notion of what are known as symmetric and Hermitian. Symmetric and Hermitian matrices. So let us say A is a real matrix, n cross n real matrix. We say symmetric, A is symmetric if A equals A transpose, that is, this is symmetric if A equals A transpose. That implies take any element Aij that is equal to Aj for all pairs I comma j. Okay. So, basically for a symmetric matrix we must have that A equals A transpose, and naturally that implies this must be a square matrix, alright, because only the symmetry is only preserved if the matrix is a square matrix. Okay. And it is Hermitian or a Hermitian symmetric matrix, Hermitian if A equals A Hermitian. And what is A Hermitian? Now let us say A is our matrix A11, A12, A21, A22 and so on. For the Hermitian matrix, what you have to do is you have to take the transpose and you have to take the complex conjugate of each element. So, this will be A11 conjugate. since you are taking the transpose, this becomes A21 and the conjugate of that. A21 becomes A12 and the conjugate, this is A22 and the conjugate. Okay. So, basically for the Hermitian you take transpose plus conjugate of each element. Now, A equal to A Hermitian, that is, it is Hermitian matrix, implies that Aij equals Aj conjugate, that is, this is Hermitian symmetric if A12 equals A21 conjugate and so on. Okay. So, that is, that matrix is known as a Hermitian matrix. Okay. So, this basically is a Hermitian matrix. Okay. Now, there are several interesting properties of this Hermitian and symmetric matrices. One of the most interesting properties is that the eigenvalues of both symmetric and Hermitian matrices are real. Alright. So, the first property is that the eigenvalues of Hermitian and symmetric matrices are real. These are real quantities, all right. And second property is another interesting property, eigenvectors corresponding to distinct eigenvalues, that is different eigenvalues, not the same eigenvalue, but distinct eigenvalues are orthogonal, and this is an important property. This implies that if V1 bar comma V2 bar are the eigenvectors corresponding to distinct eigenvalues lambda 1 comma lambda 2, this implies for a symmetric matrix V1 bar Hermitian, V2 bar equal to 0. This is the meaning of vectors being orthogonal, that is, two vectors are orthogonal if, that is, x1 bar x2 bar are two vectors, if they are real vectors, x1 bar transpose x2 bar is 0, if they are complex vectors, x1 bar Hermitian x2 bar equals 0, then the vectors are said to be orthogonal. Okay. So, this is orthogonality of vectors. This is an important property. In general, orthogonality of vectors is also a very important property. Okay. Now, let us go back to our earlier example to illustrate this fact. For instance, you have probably realized that if you look at our previous matrix, that is 1 1 1 minus 1, this is a symmetric matrix. You can see this is a symmetric matrix. We have A equals A transpose, and the eigenvalues, and naturally if you look at the eigenvalues equals plus or minus square root of 2, and these are real quantities. Okay. We have already seen this. All right. So, you can see that the eigenvalues of this symmetric matrix are real as given by the property. And now let us look at the eigenvectors, and we will show that the eigenvectors are orthogonal. The eigenvectors are 1, root 2, minus 1, let us call this as your V1 bar, and the other eigenvector is 1 minus 1 minus root 2. Now, since these vectors are real, you can simply take the transpose. So, this is V2 bar, because transpose or Hermitian will give the same thing for real vectors. Now, if you look at V1 bar into V2 bar, V1 bar transpose into V2 bar, that gives 1 square root of 2 minus 1 times 1 minus 1 minus root 2, which is equal to, you can clearly see, 1 minus root 2 plus 1 into root 2 minus 1, that is 1 minus 2 minus 1, which is basically 0. So, this basically is showing you that V1 bar Hermitian, V2 bar equal to 0 implies these vectors are orthogonal. Okay. All right, and that is a very interesting property, and that is arising because the matrix is symmetric. All right. So, in this module we have looked at various important and very interesting and also very important concepts of eigenvalues, eigenvectors and symmetric matrices, and these are very important because these are going to be used frequently in our discussion and the development of the framework of optimization for various applications. Thank you.